to your screen. Thank you.
Okay, terrific. Well, thanks everybody for having me today. So today we're just going to talk a little bit about actually that book that you just saw the cover of. So it's called The Feasibility of Natural Ventilation. So we're all here because I'm on the distinguished lecturer list and glad to be with all of you. You just heard the request for leadership. They just asked us to reinforce that there's sort of leadership opportunities not only in the chapter but also in the society as a whole. And you can attend TCs and all kinds of other things when you come to the annual meeting. So today we're really just going to do a quick overview of the book itself, its structure, familiarize you with kind of the applicable codes and standards when you're talking about considering natural ventilation, the key steps of evaluating outdoor air conditions, and then obviously taking a look at indoor and external heat gains to determine whether things are really feasible or not. So really this session is really focused on early phase sort of analysis to see, whether one should even pursue it or not. I know that you're in a place where natural ventilation has historically been pursued for a long period of time. But then you had some heat waves of late and some fires of late that maybe are making people think differently about sort of the whole context of, how many days of operation and whether you have to have sort of backup air conditioning systems. And those are all things that should be discussed when considering natural ventilation. So where the guide came from was from a very long time ago. I did a naturally ventilated federal building with 125,000 square feet of naturally ventilated space, and was asked by ASHRAE Journal to write that up with kind of what we had learned. And as part of that article, in comparing a couple of different naturally ventilated spaces, I basically summarized in this table 4 sort of the natural ventilation top 10 feasibility questions that were kind of, almost like a milestone gateway understanding of, if you haven't got your right outdoor air conditions, like really, like why bother killing each other, trying to make things work when the analytics aren't going to work out. And so coming off of that, I basically had a conversation with Professor Gail Brager at the Center for the Built Environment at UC Berkeley in sort of the mid-2010s. And so she told me that she was still using that article. She's like, the lead researcher related to the adaptive comfort standard that is often used to justify natural ventilation on the ASHRAE 55 side of things. And she was telling me in the mid 2014, 2015 time period that she was still using that article with her students in order to talk about the right way to approach natural ventilation. And I thought that was a bit of a shame that we were still using this, little 3-page article with students as representing sort of the best available information. So I paired with, my co-author, Peter Simmons, well known in ASHRAE, and we decided to compile all of the additional research that we had, as well as sort of our experience, cross-reference the standards, and I'll explain why that is an important part of the guide, and then take this gateway milestone methodology and kind of blow it up into what do you do within each of those milestones? What are the intermediate steps? So just so that we're all talking about it at the same place, most of the images are from the guide itself. We do have permission from ASHRAE to present them here to you in that context. So just as a recap, mechanisms of natural ventilation have to do with air moves when you have pressure differential. You can either have it by having wind-driven ventilation across the building, or you can have it by having buoyancy-driven natural ventilation coming from stack effect. And stack effect obviously has to do with the different density of air, and so the driving force associated with stack effect, especially in single-story spaces, is significantly less than you might expect from a wind-driven effect. So natural ventilation is not a new thing. It's actually a very old thing. Back when people couldn't rely on air conditioning, they had to rely on things like natural ventilation or mechanical ventilation without any air conditioning. or refrigerant-based cooling. So this is just, I love this little, excerpt from, a book by Robert Boyle back in 1899, right, where his primary concern was, to basically create healthy learning spaces for students. Because if you kind of sort of look deep down in here, right at the bottom here, it says, in his little sketch, what does red represent? It says represents the products of respiration from infected scholars. So all of us who have sort of lived through, the last 2.5 years of COVID, 3 years of COVID here, we know what this is all about. We know what he was trying to get to. And a large part of our profession is related to creating healthy environments by introducing ventilation. And in those days, it was natural ventilation. So stating the obvious, right, there are some really key principles that, sometimes when we work with folks, who are trying to make beautiful places, they kind of forget sort of the actual physics around natural ventilation. But in summary, natural ventilation only works if there's two openings or a really, really tall opening that effectively acts as a two-way opening. The amount of the airflow that is allowed to occur in a naturally ventilated space is controlled by the size of the smallest opening. So folks who have giant glass windows, that you can open up and get a lot of square footage, and then like have a teeny tiny chimney in the middle of the building that they think is everything is going to kind of go up to the roof, that may be the bottleneck, the size of that chimney that you're relying on. And then last but not least, air will always follow the path of least resistance. And I'll show you some diagrams a little bit later about how we need to make sure, especially when we have sort of common atria, that the top floor of the building is not the path of least resistance versus some skylight that might be at the top of the atrium. We'll get to that in just a second. So, when we come back and we talk about natural ventilation, it's kind of one of those words that's bandied about a bit, depending on where you are in the world. Basically, it just means you're getting air in through sort of an outdoor, orifice of some sort. But what ASHRAE has really tried to do is try to split the definition of natural ventilation using the traditional language of ventilation to refer to incoming outside air, which is there to support dilution of body odor and minimum outside air quantities, right? Just like ASHRAE 62. And they started to use the language of natural conditioning, and then modified even further to talk about the amounts of air from outside that you need to get in order to ensure comfort conditioning and the absorption of heat for comfort, i.e. cooling, from a natural conditioning point of view. And that is covered by ASHRAE 55. So it's really important to kind of keep the two of them separate because the language is different and then the requirements are different, which we'll kind of go over in just a second. So when we talk about then more generally sort of natural codes and standards, you can see the ones that at least were in effect at the time that we wrote the guide. And it's fairly similar that they're kind of been tracking through in the newer updates as they have come out. And so, one of the things that the guide does is it helps with these cross-referencing because you have to comply with some aspects in ASHRAE 62.1, some aspects in ASHRAE 55, some aspects in your kind of local building energy codes and standards. For example, in California, the mechanical code talks about natural ventilation and the energy code talks about natural ventilation. LEED has some aspects about natural ventilation that do not identically match up to any of the other ones. And then all of them come back to the two great granddaddies of them all, which are actually from the Chartered Institute of Building Services Engineers, which is AM10, manual AM10 and manual AM13 for mixed mode. And so LEED actually refers back to those standards. ASHRAE 55 and ASHRAE 62.1 draw from some of the principles in those standards. So those are really kind of the source understanding related to natural ventilation that everybody else is building upon. So, I just mentioned mixed mode with AM13. One of the things that we need to bear in mind is it's perfectly fine to have a mixed mode space. That doesn't necessarily mean that you can take advantage of the ASHRAE 55 adaptive comfort standard. So what we have up on the screen is a graphic that's from Gail Brager at the Center for the Built Environment. And what it does is it clarifies, which types of natural ventilation are allowed to use the adaptive comfort standard. So when we have concurrent mixed mode design, i.e. we have ventilation coming in from the outside for helping with traditional ASHRAE 62 ventilation, breathing, all of that. And you have something like a radiant panel or some other cooling system in the space, that is considered concurrent mixed mode ventilation, and that is not allowed to apply an adaptive comfort standard. Similarly, when you have changeover, like seasonal changeover, where the space could be naturally ventilated when it's nice out, but then you seal up the space and you turn on the air conditioning, those spaces also during their naturally ventilated periods of time are not allowed to take advantage of the adaptive comfort standard with regards to energy modeling or things like that. And that's because people always know in those spaces that all they got to do is flip a switch or call down to facilities and they're able to basically get electricity based cooling. So, but if you have a zone design where clearly you have maybe conference rooms on the interior of a space that have some kind of conditioning, but all the perimeter areas, they don't even have any grills or anything associated with cooling, those areas are allowed to apply the adaptive comfort standards. So that's just something to bear in mind, right? Because the adaptive comfort standard is gonna sort of, and I'll talk about that in a minute, expand sort of the range of allowable indoor temperatures. So coming back to that original article, what we had was this chart that you see up on the screen here. I'm not going to go through each of them because we're going to go through them in more detail in the context of the book. But this is where it all came from. And what you can see here, it's the same things as you would consider in your normal design for HVAC. Like, how do I control building envelope heat? How do I control internal heat? But then it really comes down to, instead of being able to guarantee a supply air temperature, you're very dependent not only on your maximum temperatures outside, which is your weather normals, but how often you're above, what would be considered normal comfort temperatures. So we're going to sort of dissect that, but we basically took those ideas from the top 10, rules of thumb and sort of brought it into this gateway approach. And so this is essentially almost like a table of contents with regards to how each of the chapters are laid out. And just so that you can read it a little bit better than within that graphic, these are essentially the guide's chapter names, right? The first one beginning, when do you not pursue natural ventilation? Because I think that's the question that people forget a lot to ask at the beginning of a design. And that doesn't have to do with outside air temperatures or anything like that. It has fundamentally to do with how you want the spaces to operate and any constraints with regards to acoustics or dust mitigation or pressurization that might be there. So we're just going to go through these real quick, make you aware of kind of what's in the guide, and along the way kind of tell you how you sort of navigate through these things. Obviously, we only have an hour together, so I'm just kind of introducing the big concepts, and if you want to get into more specific detail, obviously the guide's available to all ASHRAE members, right, for purchase. First question is when not to pursue natural ventilation. So as I said, if there are strict filtration requirements like in hospitals or clinics or art galleries, things like that, obviously those types of spaces you can't really control particulate matter or gaseous contaminants if you're open to the outdoors. So then it's really a question of how good is your outdoor air quality to decide whether under those circumstances you would want to be having openings directly to the outdoors. The other thing that you might, consider is, are there any contaminant dilution concerns like laboratory spaces? Are there any special pressurization relationships that you have to maintain in order to ensure sort of inflow for odors or inflow for containment of contaminants? The other thing, naturally ventilated spaces tend to be very open because you have to get air in the window and all across the entire floor plate. And so what that means is if you have open plan seating, there might be speech privacy concerns additionally, because you don't get that kind of background hiss coming off of the air moving across the edges of diffusers. You don't have that sort of white noise which masks speech intelligibility. So sometimes people get uncomfortable in naturally ventilated spaces related to speech privacy. And then last but not least, obviously we have our internal load heat demands, and whether they're low enough that they stay within the heat absorption capacity of incoming outside air based on incoming outside air temperatures when they're highest. So the CIBZ guide, basically has this chart that indicates how much internal load absorption can be accommodated based on a temperature differential between outside air and inside air, and then obviously based on air changes an hour. Now, with natural ventilation, we can't just tune up and down the air changes an hour, and that's why we generally tend to use dynamic analysis, bulk modeling analysis, in order to see if our naturally ventilated spaces will work. Generally speaking, as a rule of thumb, if you can keep your cooling loads to less than 2.5 watts a square foot, natural ventilation will work. If you can engage some thermal mass, maybe you have exposed concrete ceilings or exposed concrete floors, ceilings work better than floors. You can maybe eke that up to about 4 watts a square foot. Once you're higher than that, you really do have to fall back onto, our more familiar air conditioning or passive conditioning types of radiant systems. So now the other thing besides are the types of spaces that would be eligible for natural ventilation, what we always need to do in the early phases when talking about natural ventilation is to make sure that our client is on board, and not just on board with the idea that this is a sustainable solution, but with the actual practicalities, that there are some perceived benefits and there are some perceived risks associated with natural ventilation. And this is just a sample little chart. These are not the only sort of topics that you want to talk about with a client, but in terms of a little scorecard, I would say that these 3 topics of internal conditions, occupant discretion, and the cost of ownership always come up in the conversations when it comes to talking about natural ventilation with clients. And there's always 2 sides of each of those topics, right? That the perceived benefit of related to indoor conditions is you have, theoretically, if you have good outdoor air conditions, you have improved environmental quality, but the perceived risk is that you might lose comfort on some of those hotter days. With regards to occupant discretion, who has control over the operable elements in the wall? Is there a hierarchy there, or a situational constraint that would not allow everybody to have access to that decision making? Or are there situational constraints, cultural constraints, whereby some people are not allowed to adjust their clothing in order to take advantage of, sort of lightening their CLO value, in order to respond to warmer temperatures outside? And then last but not least, related to the cost of ownership, it's really kind of the perceived benefit of improved market value, because, generally speaking, people can get higher lease fees, and sometimes higher lease rates for naturally ventilated spaces, especially post-COVID. But there's the operational risk of having these openings. What does that mean for security? What does that mean when you do have those fire days or those high wind days, about the additional cost of, maintenance for dust getting into the building or soot getting into the building, right? So these are the types of things that have to be talked about up front. And so in the guide, what we do is we break down some of the greatest arguments on either side and put it in each of these seesaws in order to just kind of talk through, and you as engineers can sort of preemptively know that these are the most frequent arguments that people have. And what really needs to happen is all the subsequent steps are really done in order to dig into the analytics that would help to answer for the client, well, how many days are we losing on the comfort side, and how much better is the environmental quality by doing these assessments? And similarly, the key questions with regards to, device control and situational context, and then the typical kind of conversations that you might have about market value and operational risk. And a lot of times on this one, it's very heavily influenced about whether it's a developer that's going to hold for a long period of time, or an institutional owner that's going to hold for a long period of time, where they can see learning outcomes, healing outcomes, other types of things that improve market value for them, versus developers that might be just building to flip or to sell off. So, so once you got your client on board and everything's hunky-dory and you're going to move forward, then the next thing you just need to make sure is that you're in the right place. So ASHRAE 62.1 does require that we do a quick check on whether the area of the project is falling into a sort of a good air quality location. And so the way that they handle that is you're asked to go check how you're doing against the National Ambient Air Quality Survey for your county, basically, to see if you have any contaminants that are designated as non-attainment, which means not attaining the allowable outdoor air quality thresholds, right? And so you can see through the colorization of the map on the right-hand side there, where the little pockets are, where some aspect of outdoor air quality is such that they're not even meeting outdoor air quality conditions, much less bringing it into indoors without any filtration. And then on the left-hand side, what you can see here is sort of a chart from the book that compares the outdoor air quality standards to the World Health Organization guidelines for indoor exposures. And so you can kind of see there where there are differences. Obviously, internally, the criteria are much stricter, which is why starting by checking your non-attainment and making sure that your client is aware of that non-attainment before moving forward with natural ventilation is very important. Then the other thing that you really need to do is you need to see, hey, is wind-driven ventilation a possibility for us? These are graphs from, Los Angeles, where we've got, I'm from Los Angeles, and so we've got a very strong offshore wind condition, very predictable from, the Southwest there. And so, so that would make me in Los Angeles maybe design wind capture devices or orient a building with the location of its windows in a particular way that may be very different than what I would do if I had a sort of a more diverse wind rows to manage. The other thing, obviously, that we need to look at is both the monthly average maximums and monthly average minimums in order to see kind of what those ranges are, because what we tend to see is that in the adaptive comfort standard in ASHRAE 55, people kind of accommodate the rising of their acceptable indoor comfort temperatures in naturally ventilated spaces based on sort of how those outdoor temperature rises, because there's some both physiological effect by you dressing appropriate to the outdoor air conditions, but also psychological effect whereby people understand that if it's hot outside, it can't be less hot inside than outside if all you're doing is relying on outside air to cool you off. And then the other thing is, doing a quick psychometric frequency of occurrence check. This tool from UCLA is free and available in the public domain to, pick, both adaptive comfort ventilation and then sort of fan force ventilation, like ceiling fans, in order to see kind of what percentage of your occupied hours you might have that would be eligible to be having natural ventilation. And that starts to tell you and the owner in that cost of ownership question, well, is it worth buying all of those operable element devices? Because, operable windows are more expensive than fixed glazing windows. And then sort of the security management around making sure that, they get closed at the right times. Is that all worth it if you got only 10% of your daytime hours that is eligible, or 30% or 40%, you know, these are conversations that you really need to have, because it's an investment, not just first cost, but also sort of long-term maintenance cost. And then obviously when we're looking at the frequency of occurrence, that's of the outdoor air, you can also look at historical weather trends to see if those are sort of mapping as well, and do a quick count of how many days of outdoor conditions, if they just came indoors without any heat absorption, how many of those would just automatically off the top be too cold, too hot, good, or good with, you know, that overhead fan helping you out on the convective side. That's a starting point, because that's all this information is easy to get your hands on off of, you know, Energy Plus Weather website and other places in order to do these analyses very quickly. Then if everybody agrees that they want to go for that sort of route, then the next thing I would recommend from a professional integrity point of view is to look at kind of what an IPCC projection of likely, you know, 2050, 2100 temperature increases might be arising from global warming. It is possible from certain predominant sort of energy analysis software vendors to purchase sort of known as climate shifted EPW files in order to be able to run an 8760 shifted weather file that looks forward instead of looking backwards for the last 30 years, right? It looks forward 30 years, so that you can just at least have that conversation with your owner about what their likely future energy use is going to be, how big the coil should be, or what space you should leave in to swap out your coils in order to accommodate increased temperatures in the future. Because, you know, they could go up, you know, 3 degrees C the way that, you know, if we all follow business as usual, we don't have severe decarbonization. So those are to some extent baked in as a warming climate, that we have to know that makes it much more difficult in certain places to do natural ventilation. In northern latitudes, however, it means that you'll have more days that you might be able to have available for natural ventilation. Then if you all agree that, you know, you're in the right place, you're okay for the future, we're going to go forward, then it really becomes a question of coordinating with the architects. Make sure you have those right openings in the right places. And so, you know, this often comes back to sort of our understanding of fluid dynamics and, you know, buoyancy. These are diagrams that just help to explain to other people how air moves through a building. It's quite common that you'll see these types of diagrams at early phases in order to start testing whether you have adequate sort of sizes of incoming openings versus outgoing openings under wind conditions, under buoyancy conditions, and really make sure that everybody's understanding on the team the physics of how air moves through a building. And then once people understand the physics around that, then you start to be able to do the design and do the analysis to support it and start tweaking the sizes of the windows or other openings accordingly. So when we talk about window openings, right, we also have to talk about understanding how windows themselves, based on how they open, actually create different, you know, sort of square feet of openness versus square feet of, you know, glass is very different depending on the mechanism that window uses, right? And so when we're talking about natural ventilation openings, we're talking about the openness of them. And so if we just kind of go through a few of these, you know, the one in the upper left, nice big window, accessible to everyone. That's terrific. Then in the lower left, that's an overhead window that people can't get to. So then you have to start looking at chain actuators in order to open maybe they're high up in an atrium in order to let that hot air back out in a buoyancy driven kind of approach. these center hung windows that you can see in the middle here on the left side of the middle, like these basically act as two-way openings. They're tall enough that cooler air can come in the top, and hot air that stacks down from the ceiling can leave by the top. And then, you know, one of the things, and these kind of show up in all different ways. The one with the purple shade, you know, I just highlight there that shading devices versus natural ventilation openings is always sort of fraught with conversation, right? Because just because you're able to get outside air in and the outside air is cool enough, if you have low angle sun and you have glare and you have direct solar gain and you haven't done anything outside to, you know, cut the load, you know, you can pretty much blow up your internal heat loads effectively by not having people protected from direct solar gains. But then, you know, a lot of times once you put in those shading devices, then they like flap all around, or you can't have the shading device down while you have the window open if it swings in. So these are just some things to bear in mind as you're sort of cycling through the possibilities with an architectural team about how the actual windows themselves or the openings themselves, you know, can actually get implemented. And then, you know, when we have skylights, you know, how do you get to them? You know, are those also some kind of chain operator or motorized operator, and making sure that you're covered on a, you know, weatherproofing point of view is important. In high-rise buildings, you will be limited in most code regimes to only a 4-inch opening if it's within the height of a person's hand being able to get to it, or an 8-inch opening if it's well over their head. And that's just because they want to be very careful about people not accidentally dropping things off of, you know, out of windows in a high-rise situation, and then, you know, falling under acceleration to hurt somebody down on the sidewalks below. So just some things to think about there. In the middle right-hand side, that's a jalousie window. That basically has no seal. So even when it's closed, it's just two pieces of raw glass that are kind of sitting next to each other in kind of a shingled manner. So if you're not already in a temperate climate like, you know, Hawaii, you know, it's really hard to get any seal for the cold periods when people suggest windows like that. And then last but not least, you know, we have to remind folks that you don't have to have, you know, glass to be an operable element. This little kind of door, you know, louver kind of combination obviously worked for these folks. I don't know that's practical everywhere, but it just serves to remind us that there's other ways for us to handle getting air into a building. So if you're able to figure out all of that and you have the right openings of the right sizes that you think will probably work, then you got to come back and understand whether you comply with ASHRAE 62.1 or not. Because the first thing you have to make sure is that you're getting enough ventilation air into the building in order to meet the equivalent, you know, CFM per square foot that you would have had to meet, you know, by doing the sort of lookup table of whether it's, you know, 0.5 CFM per square foot or, you know, any of those other CFMs that are basically listed in ASHRAE 62.1. And so within ASHRAE 62.1, it gives you a number of different paths. The prescriptive zone path from 2016 and earlier, which was, you know, 4% of the total area, floor area as being your opening area, that is no longer applicable. That was written out of the ASHRAE Standard 62 the last time it was revised, because nobody on the committee could find any evidence of where that 4% ever came from originally. So really it was a rule of thumb that was unsubstantiated. And so they basically have the opportunity to either do a prescriptive zone approach or path A, which is essentially a lookup table where others have kind of pre-calculated on a single zone only, you know, how that buoyancy driven work would occur. Or you can basically model a prescriptive multi-zone, a single cell building sort of stacked up using the AM10 analysis from the CIBSE standard. Or you can do an engineered system performance approach, which is actually a dynamic bulk heat transfer, and a dynamic airflow modeling model. And so there's a lot of different softwares that can help with that in order to get you through the engineered system compliance path. So if you did that, you know, the kind of more sophisticated analysis, you would end up getting, you know, results that look something like this, where this is, you know, basically a natural ventilation for a single zone. It's, I think it was an office space. And so you can see we close the windows at night, so that's why you get these zeroed out. But then during the rest of the days for this given month, in June, you can see that the peaks that we get for the airflow coming into the space are well above the requirements of the threshold CFM, whether it's for ASHRAE 62 or some other threshold that might be local to your jurisdiction. So basically plotting this and then plotting, you know, the line that you're trying to comply with is how you demonstrate that you do comply. I suggest that people do this in all 4 seasons to make sure that it works, because sometimes, you know, if it's cold out and you aren't opening the windows as much as you might, you can run the risk of not reaching the thresholds. Now, when we talk about then modeling in ASHRAE 90.1, like how do we take advantage of all of this pre-cooling that's coming in with the outside air? Essentially, what ASHRAE 90.1 says is that you have to model as if there's a hybrid system where you're allowed to use the natural ventilation as your primary cooling system. But in cases where you're not able to control temperature in the thermal zone and can't guarantee the temperature in the thermal zone, you would need to provide air conditioning. Similarly, in ASHRAE 62.1, if you can't guarantee across an 8760 sort of weather strip that you're going to meet your ventilation requirements, you have to have a backup, you know, basically mechanical ventilation system that meets all the other requirements of ASHRAE 62.1. So these are things that, you know, we just need to bear in mind when you're doing that modeling. You have to set it up so that those fans do come on and off in response to those hours when you have proven elsewhere that you aren't able to meet that thermal or ventilation threshold. I'll skip Title 24. For LEED, so LEED is quite old in terms of its reference guide with regards to how natural ventilation is handled. It's still back in 2013. And so essentially LEED just requires that you follow the flow charts that are available in the CIBSE manuals in order to show how you have considered the key issues related to natural ventilation. And that you have designed the project to sort of reduce the exposure to exterior contaminants, right? And so there's a number of ways you can see up on the screen to sort of mix and match to get points here with regards to LEED in terms of showing compliance. So let me just kind of go on to the mixed mode spaces, and then I'll just show you kind of the little diagrams that I'm talking about. Similar to the mixed mode spaces, you know, you're basically able to get a point for using one of the strategies that's within the previous slide, and then an additional point, you know, for offering up increased ventilation when you do have the air conditioning, or sorry, when you have the mechanical ventilation available to you. And so essentially what you see on the screen here are the 2 flow charts. The one, you know, the one on the left coming from AM10 from CIBSE, and the one on the right coming from AM13. And these are available as appendices in the guide as well. So you have to go by those standards. You know, and all they're asking for is to basically track yourself through the flow chart, making sure that you're within the limits of loads and other criteria. And then that's enough for LEED in order to sort of tick the box in conjunction with showing that your outdoor air conditions are within the ASHRAE adaptive comfort band per month. So pretty straightforward for a lead, much more complicated in order to comply with ASHRAE 62 and then to do the parallel energy modeling in ASHRAE 90.1 so that sort of, especially if you're submitting for lead, they'll be very sensitive to how you've handled that on-off aspect related to the natural ventilation not complying with thermal comfort or ventilation. So then coming around to ASHRAE 55, because we've been talking about thermal comfort, right, in the context of the energy modeling. It's an interesting thing, ASHRAE 55, because it gives you a whole bunch of different ways that you can show compliance with sort of a comfort model. And the comfort models are very similar to each other, but the way that you approach them and the ranges across which you're allowed to apply them are very different. So this is a graphical method. We all have seen the modified psychrometric in the ASHRAE 55 book and elsewhere. The analytical method obviously uses these sort of bulk heat flow, dynamic heat flow transfer models that we've just been talking about, or the ASHRAE thermal comfort tool. If you then layer on top of that something that's called the elevated airspeed, which pretty much is the ceiling fans or other, directed mechanical ventilation, not to get mechanical ventilation into the building, but just, air movement around you. We all know that there's additional, a degree, 1.2 degrees that you might be able to get from that if you have exposed skin and elevated feet per minute coming across it. And then last but not least, what's historically been called the adaptive method, which is now called the naturally occupant controlled, naturally conditioned spaces method. And so if we dig into it, what you can see on the left-hand side is that, basically the different methods of proving compliance with ASHRAE 55 have different ranges for met rates and different ranges for CLO rates that you have to bear in mind. And then in addition to that, for the adaptive comfort standard or the naturally conditioned space standard, you also have to have outdoor air conditions that are between, a limited range of basically 50 to 92 degrees Fahrenheit as your mean outdoor air temperatures, right? And so if you don't have that, it's not per hour. It's like if you don't have that as your annual range, you cannot sort of apply the adaptive comfort standard to a naturally conditioned space. So these are the things that I think are just bear in mind. That as you can see on the right hand side, the air velocities, there are different limits associated with the different standards that you can apply to take advantage of the convective loss. Obviously, the blue one is the elevated speed one, where occupants don't have control, and that it's just sort of higher speeds are sort of generated. So, just you've already seen 3 different standards that you have to manage against each other. Now with an ASHRAE 55, you have to pick between these 4 different compliance types. People often think that it's going to be better for them to use the naturally conditioned path. And what I've found is that sometimes it's equally as efficient in terms of demonstrating compliance if you do have ceiling fans to show compliance on the basis of the elevated speed path, knowing that you do also have those extended ranges available to you inherently underlying the elevated speed path through the adaptive comfort standard and how people will behave in real life. And that adaptive comfort standard comes from sort of long-standing sort of Fenger analysis in the 1970s. It was reconfirmed by meta-analysis in about 2000. Dr. Gail Brager, again from the Center for the Built Environment, published in ASHRAE Journal a reconfirmation of the ranges and the establishment of the 80% and 90% acceptability rates, and reestablish these calculations to get them into the ASHRAE 55 standard. And so essentially, what we're basically asked to do is doing a rolling 7-day average on our weather tapes in order to get what these outdoor air conditions are. And then that essentially sets, at any point in time, as you compare it to your dynamic analysis and what your internal spaces are behaving at, basically allows you to compare where you stand and ensure that you're within the 80% acceptability limits across every 24-hour period. And so really the steps to analysis here are to evaluate your design against your operable element sizes that you and the architect have sort of figured out, calculate your comfort zone thresholds based on the previous slide, sort of using the adaptive comfort standard if you go that route, and then determine your comfort, right, using a dynamic thermal simulation. Once you have those two numbers, right, what you're trying to hit in terms of the comfort standard, what you're trying to hit, what you actually are achieving in terms of indoor temperature. And then you can resolve the conditions by increasing, window size iteratively, in the analysis models until you come into compliance. And so once you're able to do that, and you kind of look at each of these sort of seasons, you can see when you look at sort of a flat mean calculation where you just look at kind of where you stand versus the mean maximum, mean minimum for the month, basically, which is kind of the lead approach, versus doing sort of the rolling 7-day average. You can see here, that's what we have on two sides of this slide. The patterns are not that different. The actual numbers that are in any one of these boxes are, a little bit different. So I generally recommend to people to, if you don't are familiar with dynamic bulk heat transfer and airflow analysis, just starting with your mean minimum, mean maximum temperatures and taking those in as your outdoor air conditions to the previous adaptive comfort standard is good enough at an early phase to tell you, whether you're likely to comply or not, before, kind of really getting into the heavy duty sort of analysis. And then when you do the full heavy duty analysis, what you can basically see here is, your flat mean approach versus your fluctuating rolling 7-day average approach. They're not that different in the context of, setting the lower and upper bounds of acceptability. So that's why you can kind of use some rules of thumb just off of the flat mean approach. And then, so what you can see here is that's essentially what LEED has done on the side. They just ask you to show what is your mean temperature for the month. And so long as you fall within the range of, the 80 or 90% acceptability range, LEED will say that natural ventilation is okay. That's a bit of a cheat, but that's what the LEED points say. On the right-hand side, the Center for the Built Environment actually has an online thermal comfort tool that a lot of people use to comply with the comfort points on LEED. And it does have, excuse me, it does have an adaptive comfort standard built into it. So you can actually run a series of analyses, both under the elevated airspeed, under the adaptive comfort standard, and then under a range of the CLO and MET ranges that are within ASHRAE 55, in order to show how each of these bands basically shifts up and down associated with which comfort standard you have chosen. And you can kind of navigate their compliance path to show how you are complying with ASHRAE 55 using this, again, public domain online tool that's provided by the University of California for free. And then last but not least, as we get towards the end of our time together, in most of the time, people's perception of natural ventilation, sort of our paradigms, are coming from our homes where, we just walk over to the window, we open the window, we close the window, we're making the choice. once we get into sort of larger commercial buildings, I think, the tendency is to want to start automating things a little bit more. And then you have to have sensors in, and then you have to figure out some control sequences. And so what the last chapter of the guide basically does is it basically maps sort of and provides typical sequences of operation about, based on how you might want to automatically control certain windows, what sensors you would need and what sensor types you would need in order to get feedback, in order to have those sequences operate under stable control without people kind of like going crazy with like stuff happening around them. So I will say, for that federal building that I talked about at the beginning that led to the original article, people started moving in before the building was commissioned. And we had overly sensitive static outside air pressure sensors that were measuring the differential pressure across the building, such that every time wind changed direction, the motorized windows, which were the upper windows, they started trying to go in the reverse direction, because none of the loops had been tuned to slow things down, to basically only change window position every 15 minutes. And so the very first people who moved into the building thought the building was haunted because the windows kept moving around, and they had nothing to do with it. And so I think these are the kinds of things that we're just, Peter and I were trying to capture in the book, is these kind of real life experiences, and make sure that, the guide is there for people who might want to be pursuing natural ventilation going into the future, with just a little bit more in their arsenal. In terms of knowing what sensors you need, knowing, what the sequences are that you could use in order to use these things in a more automated way at scale. So the final takeaway is always have that conversation with your owner, understand kind of like their tolerance level on these key issues, and have these discussions like way early, before you invest a lot in analysis. Really make sure everybody on the team understands all these definitions and kind of what that means in terms of internal conditions and how often they could occur. Make sure like you've done your proper weather analysis, your wind regime, and your outdoor air quality sort of situation, because that's going to make or break you before you do any subsequent analysis. And then, and then, you have to start the harder part of the analysis, whether that be the ASHRAE 62 analysis or the ASHRAE 55 analysis, to see whether you fit into the adaptive comfort standard, and how many hours in each season you basically are, too hot, too cold, good alone, or good with that elevated airspeed, right? And so really on the right-hand side, taking your steps one by one through these gateway milestones will save you time and money if you have robust conversations each way, review your analysis each step of the way, and say, should we go on? And then the cost and the time associated with doing the subsequent analysis obviously is something to be negotiated with the owner. So that's what we've got today. I will stop sharing in order to sort of take questions here.
So thank you very much for the presentation. At this point, if anybody has any questions, we have about 3 minutes. You can either turn your camera and microphone on or put them in the chat. Okay, well, hopefully you learned a lot during this presentation. I know I did. I didn't know that the 4% was a arbitrary rule of thumb. I always wondered about that, so that's been interesting to learn for me at least. So with that, if there are no questions, actually we're getting some right now, so give me 1 second. PDH credits, unfortunately, no, we did not make the availability of that for you, but we will be looking into that for future presentations. There were a lot of links in your presentation. Erin, would we be able to get a list of those, or could you share your slides?
Yeah, we can share the slides. I would just ask people, ASHRAE allowed us to use this for the purposes of training within ASHRAE. So if you use it in that case, that's fine, but they've asked that those not be sort of replicated without people purchasing the book, basically.
Absolutely. So if you are interested in specific links, please reach out to membership and we will get you a presentation individually. This recording will be posted on our ASHRAE website within the next couple days. It takes a little bit to process, but yes, we will be posting it. And if you have any further questions, we'll include our guest's information in the video recording when we post that to the website. So with that, unless there are any other questions I'm not seeing, I'd like to thank our guests for the really great presentation, as well as all of our attendees. I hope you have a very happy holiday season, and we look forward to seeing you in the new year. Thank you, everyone. Bye-bye.